Sounds great. Okay, yeah, so welcome everybody. So welcome to another MOCM development meeting. So today, I think one of the things that we would like to do is want to highlight a bit of the current status of the MOC development. So in the past months, I think there are a few things that we would like to highlight. The first thing is that we have spent quite a bit of effort bringing more GPU diversity support. So we will have AMD GPU announced in August, as well as the Orange Pi Mali support. So thanks to all the contributors. Another thing that I think would be quite relevant is that we're also adding a bit more model diversity here. Maybe we can let Charlie to talk a bit about his work on supporting the wizard models, and David, who is also here, could talk about some of the coding model updates. So besides that, one of the things that we are pushing very hard is actually supporting formal Python API. So that is also kind of getting landed in October. So as you can see that right now we have a quite okay Python API that allows you to run things through Colab, which is quite cool. And we'll continue iterating on it. And so today, I think there are a few topics. I know that, I don't know, Jihao is not yet here, so maybe Jinglu, if you can send him a ping. I think it would be good to get Jihao to talk about his work on the inference. And then we also want to give everybody a bit of update in terms of our distributed, actually multi-GPU support. So one of the things that I think what we can do is we can first let Charlie and David and actually Casey talking about some of their works quickly, and then we will move on to Jinglu to talk about some of multi-GPU support. Maybe Charlie, can you get first in the queue? Yeah.
Yeah. So hi everyone, my name is Charlie. I am currently a master's student at Carnegie Mellon, and I've been working on MLC for the past 1 or 2 months, I think. And then some of the recent work includes supporting the Wizard LM, the Wizard family models, including the Wizard LM, which is a general chatting LM, and also the Wizard Math, which is for mathematical questions, and then also the Wizard Coder, which is, I guess, kind of similar to the Llama Coder. Yeah, and it's kind of interesting to see how there are like many specialized LLMs, and then it kind of resonates with one of our vision, which is running some local assistant that are specialized to a specific task. So there's that. And another work I'm currently trying to do is to make it easier to add new models. For instance, when trying to compile the Wizard Math model, I wasn't able to reuse the Llama 2 model, the model library. So there are some abstraction work needed to be done so that future model variants can be added more easily and smoothly. Yeah.
Sounds great. And actually, you can check out Charlie's work both in terms of Colab and the latest web LM demo. So Charlie, if you can paste some of the notebooks online here,
Okay.
that'll be good. Yeah. Then next up, we can let David talking about some of his work on coding Llama. Yeah.
Hi everyone, my name is David. I will be a visiting student at Carnegie Mellon for the next semester. And actually my work is very similar to what Charlie's been doing. I'm also like working on improving code completion models for the MLC LLM framework, and actually I've been working on putting these models available on the MLC. And yeah, that's basically it. And I think it would be interesting to explore a little bit more in order to try to decrease the time so we can put more models into MLC and somehow like have more models in the future.
Great. Thank you, David. And I think we also had latest notebooks, and hopefully we can also build up some of the demos using the coding model, which is pretty cool, actually. Yeah, maybe Casey, can you also talk a bit about your latest work in the or planning in terms of multimodality? Yeah.
Yeah. Hi everyone. I'm Catherine. So I just graduated from CMU and currently on the gap year. And yeah, so lately I'm working on bringing the Lava support to the MLC repo, and hopefully Lava will bring the like state-of-the-art like multimodal stuff. And also, yeah, because there are a lot of people working on multimodal, like for example, the Google's, I don't know if it's Google, but like the Gemini is coming soon. So like hopefully the framework can bring more multimodal support. And I think I don't know about like how's the so hopefully like in the future we can also like formalize the iOS app and then get it published. Yeah, so for this week, hopefully I can just finish bringing in the Lava support.
Sounds great. Cool. I think these are some of the highlights from the overall API sides. And next up, one of the things that we can do is Junlu, maybe you can spend a bit of 10 to 15 minutes to quickly walk everybody through some of the multi-GPU support. It's not yet landed, but I think it's coming soon. And next up, we also have Zhihao talking about some of the latest Flash inference results. Okay, Junlu, please take it away. Yeah.
Okay, great. So hey guys, my name is Junru, and I'm one of the developer in MLCLM, and I'm an open source enthusiast. And I'm also a program committee member of Apache TVM, which is the underlying compiler that MLC uses for universal deployment, which is pretty cool. And today I'm gonna quickly talk about our progress and the system design of Disco, the distributed or multi-GPU runtime that we wanted to use, integrate with MLCLM, so that we can utilize like multiple, say 4090s or multiple AMD GPUs together to do inference for larger models. Great. So today our discussion will only be limited to the runtime Disco, and the compiler construct, which is called DisIR, will be covered by Hongyi in our next community meeting. So bad news for us is that I got to know that I gotta do this presentation. I didn't know that until yesterday night, so I didn't have much time to prepare for the slides. But the good side of the good side is that we actually have a design doc which I can show us and go it through. Okay, cool. So let's talk about distributed inference on a very high level. So what is distributed inference? The thing is, we have right now large language models are really, really large. They can span over like tens of different GPUs because one GPU cannot the memory of one GPU may not fit. We wanted to utilize, the point is that we want to use multiple GPUs as they have larger memory, more compute to serve larger models like GPT-4. Right now the compiler on the compiler side is usually considered like traditional compiler, GCC, Rust. They're traditionally considered as a single on a single device, a single CPU. For example, when you use GCC, you compile something to executable that is only run on a single thread or multiple threads. So that's the difference between and the Disco runtime is supposed to expand our technology from one GPU to multiple GPUs. Anyways, I think I'm in a bit mess right now. It's fine. So let's look at how Disco works. The key concept in Disco is a session. A Disco session contains control plane and data plane. And there's one on the control plane, there's only one centralized controller, and multiple different workers like one worker, you can consider one worker like in charge of one GPU. So if there are 10 workers you're working on, you have 10 GPUs available, you can create 10 workers. And on the control plane, the single controller controls how the workers execute. So the controller can broadcast instructions, say, please load this shared library for me, and please execute this, call this function, execute this command for me. The special design of Disco is that it is SPMD, single program, multiple data. So we consider all the workers, they always execute a single set of instructions in the same order. For example, in Disco, if we let all the workers, or if we call load VM module, we are basically let all the workers to load the same module at the same time. If we create an empty ND array, it's basically asking all the workers to create the same ND array on different devices altogether. Okay, this is the control plane. And on the data plane, we are basically leveraging what is available, what is the fast solution available on market. For example, on NVIDIA GPUs, we are basically using offloading all the like data communication, like say, or reduce or broadcast gather to NCCL, NCCL, that is NVIDIA's official communication library. And on AMD GPUs, we're using RCCL, RCCL. And if there is no GPU, we could always fall back to MPI. Okay, so that's a high-level introduction of Disco. It's like single program, multiple data, single controller, multiple worker system. And how do we use Disco in MLC, in large language model inference? This is a interesting question I believe most of us care about. So in our case, in large language models, there are two major components of it. One is MLP, the feed-forward network. Another is attention, which includes QKV projection and scale dot attention. So in Disco, by default we use tensor parallelism, which is we share the weights onto multiple different GPUs. For example, if we have a weight of shape 128 by 128, then we could shard it to like 2, 4, or 8 GPUs by one of this dimension. In our case, in MLP, MLP is basically matmul plus Galil plus matmul, right? So in our case, we always shard the first dimension, the spatial dimension of the first weight, and the reduction dimension of the second weight, and then or reduce to gather the compute results. How about attention? Attention is even simpler, because attention is basically the basic architecture of attention is multi-head, meaning all the heads, they are doing like exactly the same operation but in concurrent. So we shard across a number of heads dimension. In our case, what we do is that we share the head dimension of QKV projection, and also the dimension in the scale dot attention, and also KV cache actually. And then we do or reduce after the output projection. Yep. And by I'm currently working on integrating this tensor parallelism scheme into MLC-LLM, and we're going to have this ready sometime this week. It's joint work with Hongyi. And back to the topic. After we have Disco, we are able to use multiple GPUs to do, like, say, 2 GPUs to distribute inference or infer Llama 70B on like 2 AMD GPUs. And we're going to release a demo about it sometime soon. And if you're interested in the design details of Disco, I can briefly walk you through about it as well. So just now we briefly covered how the SPMD runtime, single program, multiple data runtime works. And then let's go over its core design. The core design of this code is that it is a register-based model. It's like when we are broadcasting an instruction, say please add A and B into C. What we do on each worker is that we get the register for A and get the register for B, read them from our register file, and then calculate the results of A plus B, and then put it back on register C. Because each worker in SPMD, each worker they execute that same set of commands. The offset of register slots is actually can be pre-calculated by the controller. So in controller there is a design called dref, which which just strictly corresponds to the offset that I just mentioned, like using an integer. Say this is if register ID is 8, it means like the 8th register on each worker. Going back to our example before, A plus B, if A corresponds to the 3rd register and B corresponds to the 5th register, what we do is that we broadcast the command, say, please call this function using the 3rd register and the 5th register and store the result back to the 8th register. It is what we do on dref. And for D session, it is also a concept that is collocated with a controller that it maintains a list of registers available right now, and also maintains a command queue that allows us to effectively broadcast the commands to all the workers. Each command can be on the controller side, each command can be considered as like broadcasting one function to be called and or action to be executed, and a bunch of register IDs to be used. Let's look at a more complicated example here. This is the pipeline parallelism written in TVM Relax. Here we created, first of all, there are 2 workers, worker 0 and worker 1. And to input X, worker 0 first calculates the matrix multiplication of X by W, and then send the intermediate result to worker 1, and then worker 1 receive from worker 0 and do the subsequent matrix multiplication again and send it back. This is a really, really simplistic example of pipeline parallelism that different workers, they are on charge of different kind of computation. What we do to execute this on this code is that first we'll create a disco session of 2 workers, and then load the parameters W using get global function, which is register upward, and then we load the parameter shard for each worker correspondingly. The next step is that we load this method compiled to disk, which we say is mymod.so, and into a dref as we mentioned before, and create the results in the array, the input in the array and the result slot, which is empty. And then we copy the input to worker 0 and broadcast it to all the workers. And next step is to get this method, the decode method from the TVM module. And on each worker, they execute their own shards correspondingly. And this is the results. In the final step, we copy the result back to our to the controller. And using this presentation, we can always represent all the tensor parallelism and like 3D parallelism actually without any problem. And for large language models, they're always their inference can always be represented by tensor parallelism. So it's a subset of what this code can do. Okay, so that's basically it for our Disco functionalities, and our implementation is basically done and upstream and merged on TVM. And right now, Hongyi and I are working on like integrating Disco to MLCLM. Oh, I saw a question. What is the assumed interconnect between the GPUs? It's a great question, actually. This is basically about the data plane. That's how do each worker talk to each other. For example, when we are doing or reduce, what do we do to effectively utilize the network bandwidth? So it is determined actually by NCCL, by Nico. So if Nico detected there is an NVLink between like two GPUs, they utilize NVLink, but if not, they can always fall back to PCIe or LAN. Does it answer the question? Cool. There's another question for D. Thanks for asking. So the relationship between Relax VM and Disco, that's a great question actually. So Disco is a runtime construct that can execute multiple execute a single program in multiple workers. And the program can be, say, Python program or Relax program that we compile to a DSO file. As what we show in the example a while ago. So as you can see, this is the TVM Relax IR, which is compiled to a DSO, mymod.so, and it can be loaded by Disco runtime. So you can consider Relax is a subset of things that Disco can do. Does it make sense? Okay, great. Okay, thanks. Any questions? Okay, great.
Actually, I have a question. Yeah, thank you for the great presentation. I think I learned a lot about it. Personally, I have a question about like how we can implement the partitioning strategy. Like, will it be, can we implement some kind of like a pass to try out like implement the partitioning strategy, or like is there any like other approach to do it?
I see. This is a great question, actually. So, in general, if we wanted to optimize or distribute the workloads of any deep learning model onto multiple GPUs, there is definitely a space that we can search for the optimal partitioning strategy. There is a paper in OSDI a while ago called APA, which searches such partitioning automatically. And if it comes down to large language models, optimal strategy is actually fixed, as described by Megatron LM paper, that they always shard the spatial dimension and then reduction dimension in MLP, and always shard always shard the number of heads dimension in attention. So this strategy for LLM is actually fixed, but in general, they need to be searched. And to do the sharding itself, it's possible to implement a relaxed path, a compiler path to transform the IR into the shapes that we desire. For example, if we shard like 128 into 4 pieces, we want to transform the shape from 128 to 32, right? But from a very high level, if we wanted to shard over a mesh of devices, we will need some add-on IR design, which is described by Dista IR that Hongyu developed. For large language models right now, we can always hard code the partitioning strategy, which means Dista IR is not a strict necessity. But in general case, we will need Dista IR to make it work universally.
I see. Yeah, I see. Then like do we need separate model definition per for Disco per model then? Like in MLC element, we have like a couple of language models, right? I'm trying to understand like how this will change for Disco.
I think in this case, specifically for MLC LM, we do not need separate model definition because we could do an annotation on the parameters Say in the MLP layer, we annotate the first way to be like sharded across spatial dimension, second across reduction dimension. Annotation-based way works pretty well in my experience. So we do not have to develop a new one. But in the future, we might want to consider how to annotate more properly, like annotate SPMD device mesh onto those tensors with our the new NN.module APIs.
I see. Great. Yeah, thank you.
Great. Thanks for the question. These are great.
Thank you, Jinglu. So that's a quick overview. Hopefully we will be able to see some actions
Yeah.
in our next community meeting, which happens in some months.
Sure.
Okay, moving next, we'll have Zhihao today, and he's going to tell us a bit more about the Flash inference work. Yeah.
Oh, can you hear me?
Yes.
I can hear you now.
Oh,
Yes.
no. I have a quick slide. So yeah, today I'm gonna introduce Flash Infer. Flash Infer is my recent work that is a Flash attention kernel library for low latency and long context inference. The key innovation of Flash Infer is to use the KV parallelism, which I highlight in the title. And I'm gonna explain why we need KV parallelism and how do we implement. So to begin with, let's have a brief glance of the self-attention. Self-attention is a very key component in transformers, where we compute the dot product of Q matrix, corollary matrix, and key transpose of key matrix, and go through a softmax operator, and then multiply it by another value matrix. So the whole operator is a 3-stage. First stage is a GMM or GMV operation in case that in the decoding setting that is GMV. And the second operator is a softmax operator, and third operator is another GMV operator. So the key challenge here is a softmax operator. And if there is no softmax operator, we can safely fuse the two operators together. And let me explain why. Softmax operator to remove the numerical issues of softmax, people always use a safe softmax operator. Well, we compute the maximum of all the input logics, and then we substitute each input logic with the maximal value and compute the exponential of the pre-logics minus the maximal value. And then we compute the denominator and divide each exponential value by this denominator. That is a safe softmax operator. And later on, people find that the original softmax operator need to access the logics for 3 times. There are 3 loops altogether. And in online softmax, people find that this whole algorithm can be formulated as a 2-stage algorithm, which means we only need 2 loops, and we access the operator 2 times, access the logic 2 times. And in the first stage, we compute the accumulate maximum logics up to the current position. And the second one computes the denominator accumulated from the beginning to the current stage. And the second loop computes the final softmax value by by computing the exponential logics divided by the M and D computed in the previous stage. And Flash attention extended further by also considering the later on operators. Say Flash softmax is only the intermediate operator here, and Flash attention considers 3 operators altogether, and they find that the whole computation can be formulated as also a state update function, very similar to the online softmax. Here we have 4 states. The X is the logics, pre-softmax logics, and M and D are the states used in online submax, and O are the currently, accumulated temporal weighted temporal submax multiplied by V, the temporal aggregated results. And the flash attention operator can be formulated as the state update of these 4 states, and by looping the I from the beginning to the end of the KV length. When we parallelize the flash attention, people, for example, previous libraries always parallelize in this fashion. They firstly parallelize different heads because different heads computation are fully independent. And then they parallelize the batch dimension, say, because different batches are equivalent to different heads. They're all independent. And people also can parallelize on the query length because the query is a spatial dimension. There is no reduction on this dimension, so we can safely parallelize them. And previously, people multiply the 3 parallelizable dimensions and use different thread blocks in GPUs to execute them. So the overall number of thread blocks equals the number of heads times number of batches times query length. And for large language model inference, the issue is that the query length is only 1, and the batch size is, for example, if we want a low latency, the batch size cannot be too large. So the batch size is around 16. And the number of heads for Llama is only 32. So the multiplication of the number of heads, batch size, and query length cannot fulfill the overall number of thread blocks that can be executed, that can be launched on modern GPUs. For example, the RTX 4090 has around 5,000 available thread blocks that can be executed altogether. And for A100 or H100, the number is even larger. We can execute 1,000 thread blocks altogether. So such parallelism pattern cannot fully utilize the SMs in modern GPUs. So the way we address this issue is to parallelize on KV dimension. Say, previously we loop over the KV block by block, but all in a same thread block. But here we split the KV dimension and execute them in different thread blocks. In this way, we can multiply this parallelism factor by another number of KV trunks. And we see that previously we don't parallelize on this dimension because there are dependencies in the aggregation, in the state update of this function. But we found that the first stage, say we compute Q times K, this stage is fully independent for each KV trunk. So we can safely parallelize them all together. And actually this stage takes a most significant amount of time. And then we perform a overall grid synchronization and use the cross-thread block synchronization to update the other states at the M, D, and O. And after that, we get the final results. And we compare this implementation with previous implementations, such as the PyTorch SDPA kernel. We found that we are 3 times faster than them for long sequence. For example, when the sequence is 32K. And for smaller sequence, our performance is still or faster than the SDPA implementation. But this figure we cannot see because the time duration for short sequence is too small. And we also have other features. For example, we support low precision KV cache. Now we already support FP8 KV cache with E4M3 and E5M2 data type. And we also fuse the flash implementation with rotary embeddings. And here you can see that by fusing the rotary embedding, the execution time doesn't change at all, because the computation of the flash infer decoding is totally IO bound. And after fusing with rotary embedding, the GPU time only doesn't increase at all. And we can fulfill the memory bandwidth when sequence length is large. For example, when Zoox length is 10K, we can nearly achieve the full memory bandwidth. And Yasin from OKML helped me integrate the flash info implementation with MLCLM on A10G instance provided by the AWS, we can achieve significantly faster decoding speed. Yeah. And more news are coming in this week and next week. We are gonna writing a blog post about how to deploying 32K large language models on a single consumer GPUs. And we will release a flash info wrapper, which is a purely C++ plan, which we can integrate with other frameworks. And yeah, that's it. Thank you everyone for listening.
Sounds great. Thank you, Jihao. And I'm really looking forward for us to getting long contacts coming. And sounds like a lot of new results coming in the next months. Okay, so now let's move on to more like open discussion session. In terms of roadmaps coming up, I know that we have some exciting works on pushing for the distributed support. And Rehan, maybe you can talk a bit about our current ongoing effort on bringing in the batching support, and then we can open the mic for everybody to chime in. Okay, maybe Rehan, you can say a few words. Yeah.
Yeah, sure. Hello, folks. So for running late a little bit, and I didn't prepare anything like slides, but just happy to share with folks that with the news that we are currently pushing the effort on MLC-LN for batching. So currently we are doing some thrust on things like KV cache, and after that we will have some integration with MLC-LN together with the host flash info algorithm, like or kernel support. And after that we will gradually bring things like continuous batching stuff to the MLC-LN code base, and we expect this to happen just within this month. So folks, please stay tuned.
Sounds great. Okay, so I think now that's the most of the things for today. We can try to open the mic to see if anybody in the room would like to raise your hands and share something else. Yeah, Sing.
Sure. I actually have a question, which wasn't really resolved by the community members. You talk about in this session both parallelism and also batch inference.
Right.
Is either one of them actually facilitate the one GPU to do two inference at the same time? That's
yeah,
not
so
yeah.
The batching part is try to serve that goal. Yeah.
Okay, but then the memory has to manage somehow because there's just
Exactly.
like most. Okay, cool. And the second one is, well, first of all, congratulations. I'm actually seeing community member using your output to produce new things, which is quite incredible given that the history of the project, and it's only 0.2, you already have an ecosystem, although they're not very sophisticated application, but they're actually building on top of what you guys are outputting. This is just incredible. Congratulations. The second part is somewhat tied up to that, and it's with embeddings. I've noticed that we've finally got that embedding PL solved, that problem solved. They still haven't merged it, but we have it now in Python. What I wanted to do is try to get it to JavaScript, but I'm not quite clear on exactly what was done in Python to bypass that problem, whether we can like do it to JavaScript, because as you're aware, there are a lot of application developers who are basically relying on embedding out there that are kind of working with LLMs right now. Yeah,
that's a great point. So Deep, who worked on some of the embedding support, actually is not here.
Okay.
But what we can do is we can bring it back to him, and I think Rehan, you can also coordinate a bit. And I think there are multiple paths on bringing embeddings. One thing is we can try to bring it to the web LLM, right? So that's like one possible route. Another possible route is trying to patch up the REST API so that we can work for effectively make sure the REST API support embeddings. And I agree, like embedding plus language model would be something that's pretty cool because it enables things like document retrieval and other
Yeah,
applications.
that's a
Yeah,
lot.
great point. Yeah,
Thank you.
cool.
Hello. Yeah, I got two questions about the roadmap. So the first one, now we already have Disco, and is there any specific time point that we can see a distributed version of large model in MLC? So another question is there any plan to support the compilation pipeline to like lower the distributed IR to Disco? So
that's a great point. And by the way, I did see you are the one that brings up the discussion on Disco IR, right? So on this side.
Yeah,
Yes.
just some initial
participating.
thought.
Yeah, so I think Hongyi is also here, so you guys should definitely connect also through Discord as well. To answer your question, first for the Disco is a low-level runtime, right? So that allows us to effectively offload some SPMD workload. So right now the strategy we are having is we try to build a bottom up, which means that you do the lowest level, you go up and graduate up. And I think there are a lot of flexibilities that we can offer in terms of how we want to lower, right? And I think that the goal of Unity is not trying to have a strong opinion on, hey, here's exactly how you do that. We want to offer flexibility so that you will be able to do different things. In terms of this IR, I think this is something that we are pushing for. The first milestone would be multi-GPU and effectively no disk IR, and we're going to push it up, bring this IR support. And then I think the Disco runtime should be able to support distributed as long as we will be able to have a worker launcher that set up in Echo. So I feel like the gap from multi-GPU to distributed wouldn't be that high, but indeed it would be a bit of engineering. If you're interested in contributing, I think definitely talk to Jinglu. My feeling is that if you have a distributed launcher, like you launch workers, right? You connect a controller to the worker, and you set up an echo, and that's it. So when we have existing MPI environment, it should be something that's doable. Yeah. Does that answer your question? Yeah.
Actually, another question is I'm looking for a specific time point that we can use distributed version of like Llama or ChatGPT. Is there anybody is doing it on that, or if not, we can contribute a bit.
Yes. So I think one concrete timeline is in 1 month, we're going to see at least a multi-GPU version. Okay.
Thank you.
My expectation is the gap from multi-GPU version to distributed is what we described, right? So I think that lift is not that high, but it's indeed a lift. If I'm interested in contributing, we are definitely love to iterate together in a community. And I think there are a lot of opportunities because Disco is not trying to replace existing distributed runtime. For example, you could launch Disco within, say, Spark or within Kubernetes, right? Because it's just you just need a way to be able to start your work and connect things together. So that's the intention to allow us to be more flexible in here. Yeah. And thank you for bringing it up, and we love more discussion here. Yeah. And there's a question about batching support. And I think Ruihan already answered the question, but yes, Ham, do please bring up this on the Discuss forum as well. We'd love to continue discussion there. And I do think that Ruihan is going to also help us to publishing update documents. Yeah. Okay.
Right.
Sounds great. Any other more points? Okay, if not, thank you everybody for coming. We are going to have another community meeting in a month. And hopefully, let's see if we can fulfill our plannings. But depending on our trajectory of the past, hopefully we will have something to show like this month. Cool. Thank you, everybody, and looking forward to bringing more things. Yeah.